In the second part of Chapter 10, we have a lot of ground to cover here. There's a lot of slides, but should go fairly quickly. Lewis structures, however, cover covalent bonding quite nicely. While you won't see ionic bonding represented by Lewis structures very often, you will almost always see covalent structures represented by Lewis structures, particularly when you get to organic chemistry. The idea of being able to write a Lewis structure for a covalent compound and then the idea of resonance become very important to these covalent organic compounds. So remember, in covalent structures, electrons are being shared when nonmetals bond to other nonmetals. The molecular compounds have what are known as these covalent bonds where electrons are being shared. So we're just restating everything that we've already seen, just driving that home. And in Lewis theory, we are, instead of showing the transfer of electrons from one to the other, we're going to represent our covalent bonding by allowing neighboring atoms to share their valence electrons. Okay? So what we're going to do is draw the Lewis structure for individual atoms and then bring those together and show them almost as an overlap or a sharing of those particular valence electrons. So what we're trying to do again is share in order to get an octet or a duet for the case of hydrogen, sometimes lithium and beryllium. Remember those two as well, because sometimes that may come into play for them. They may not need a full octet. When we are doing this, when we are sharing electrons, shared electrons get counted for both of the atoms. So when an electron is between two structures, both of them get to claim that electron. For example, water, classic Lewis structure for a covalent compound. Hydrogen has this Lewis structure, oxygen has this Lewis structure. In water, we know it's H2O, so each hydrogen and the oxygen will share their electrons so that each hydrogen atom gets the duet. So these two electrons that are between the hydrogen and oxygen, hydrogen counts both of them to complete its duet, but oxygen also gets to claim those two in order to up its count. Same thing here. These two, hydrogen is claiming both of them as its duet, but oxygen is also claiming both electrons, both the one that it started with originally and the one that it's sharing with the hydrogen. The hydrogens count the one that it had originally, plus the one that's being shared with the oxygen. So those electrons kind of get counted as twofers, if you will. They get counted for both of the atoms that are sharing them. Okay, so here's another way to look at that. The shared electrons count toward both of them, so you can draw circles around the electrons in order to look at the overlap. Anywhere in the overlap, that gets counted for both. Okay, so the oxygen has the full octet, each hydrogen has its duet in this case. Now, when you share electrons between two atoms, that is what's known as a bonding pair of electrons. That is what creates the bond that holds those atoms together. If you have electrons that are only on one atom and they're not being associated between two atoms, those are known as lone pair or non-bonding electrons. So you have bonding pairs and lone pairs. Now, bonding pairs, it gets a little confusing just having all these dots floating around. You start really seeing spots after a while. So don't try to do this if you're too near a Dalmatian. It will really mess with your head. Just joking. Bonding pairs of electrons, very often in order to simplify the visual representation of the structure, will get represented by a dash between the atoms to represent a chemical bond. If you are going to do this, remember that each dash represents a pair of shared electrons. So this is the equivalent of those two dots. This is the equivalent of the two dots that we had. Okay, so that's what's being represented by those dashes. That indicates a bonding pair of electrons. Every dash counts as two electrons. Okay, so one dash equals two electrons. And this is the abbreviation right here, E with a superscripted negative, that's the abbreviation for electron. So I don't know if I have explained that yet or not at any point, but wanted to be sure and do that. So Lewis theory can help us explain why we have those diatomic molecules. Remember that the halogens, chlorine, bromine, iodine, form diatomic molecules. So when they exist in nature, it's Br2, I2, Cl2. We've also got H2 and O2. You know, this is helping to explain why those exist in a diatomic form and not just as individual elements. So starting with chlorine, starting with the halogens here, okay, because I included a couple here that weren't halogens, so focus on the halogens. If two chlorine atoms pair together, each one of them needs only one electron to complete the octet. It's got this one lone electron here. So if each one of them shares that lone electron, they can attain an octet. Okay, they can have a bonding pair of electrons here. Remember, that represents 2 electrons. So we find that elemental chlorine does exist in a diatomic molecule, which is what Lewis theory would predict. Same thing for the other halogens. You can draw them the exact same way. Hydrogen, same thing. It's got that one electron. It wants to share them to make a duet. So I can put a bond in between them. In nature, it's a diatomic. So we can run through all the diatomics. Here's the oxygen. Oxygen exists as a diatomic. Now this one's a little bit different. It seems like it really wouldn't be an advantage for that oxygen to share one bonding pair of electrons because each one of them is still going to have an odd man out. Okay, so this one's a little bit different. But what's going on with oxygen is, okay, if we start with the 2 individual Lewis structures, okay, and we try to write a Lewis structure for it, we still don't have enough electrons here to give each oxygen atom an octet. So I've shared one pair in between, and then I've actually transferred. So this is a combination of ionic and covalent here. We took one electron and we just donated it over here to the other one to fill that one, and then it shared these 2. That's kind of what it's showing here. That doesn't work really well because one oxygen gets an octet, but the other one is still very unhappy. He doesn't have an octet. He needs to finish that out. So we can convert one of the lone pairs of electrons here. Instead of transferring that electron, I can share all those electrons as well. So what they're going to do is they're both going to share those 2 lone electrons. Okay? And so I end up with a structure that looks like this, or if I draw those bonding electrons as dashes instead of dots, I get what is known as a double bond. I draw 2 dashes. Okay, that's the equivalent of 4 electrons, 2 bonding pairs of electrons, 4 electrons total. So this explains why oxygen creates a diatomic molecule. It can share more than just 2 electrons and gain a stable structure. So if I show the overlap, each oxygen atom now has an octet. Okay, both are full, both are happy. Nitrogen, okay, if we think about this one, if we start with individual nitrogens, and they haven't drawn it here, so I'm just using the empty space here. So if I start, I have 5 valence electrons, 1, 2, 3, 4, 5. I've got 3 lone electrons here that each need to share. If I draw another one this way, here's 3 right here. Well, if I pull all those together, then the electrons can go in between to satisfy the octet for both nitrogens. They can just pair up those lone electrons or convert 2 lone pairs of electrons into bonding pairs. And what happens is we now get a triple bond. We get 3 dashes that indicates 6 electrons are being shared between those 2 nitrogen atoms. So if I'm able to, I can keep pulling lone pairs of electrons in to form bonding pairs of electrons to satisfy those octets. I can share pretty much as I need to, up to about a triple bond. Now, by the time you get to something, you know, if you have carbon, for example, instead of two carbons coming together and pooling all of their electrons and forming maybe a quadruple bond, carbon tends to look for other things to bond to. It keeps binding sites. So you're never going to get all 4 electrons on a carbon being shared with, say, another carbon. But you can share up to 3 of those, 6 electrons between the two. All right, so just to reiterate what I was talking about. When you have 2 electron pairs being shared between 2 atoms, so a total of 4 electrons, 2 electron pairs is 4 electrons. Okay. That is known as a double bond. Now, if you were able to actually see those bonds and measure them, you would see that double bonds, because you've got more electrons and they're drawing it together, they tend to be shorter and stronger than single bonds. So if you think of it as a single bungee cord holding 2 things together that are the same mass, that one bungee cord is probably going to be pulled harder. It's going to stretch out longer, and it is probably going to snap a little bit quicker, whereas if I put 2 bungee cords between something, the same 2 things, they're going to pull it closer together, so they're not going to be stretched out as much. They'll be shorter. It creates a stronger weld or bond, if you will, between those 2 objects because the 2 are working together. Okay, same thing for a double bond. So if you were able to actually measure the distance between the nucleus of an oxygen atom, between 2 oxygen nuclei in an oxygen-oxygen double bond, you would find that it is 121 picometers. Okay, so very small, but you can measure that. 121 picometers. If you measured a single bond between 2 oxygen atoms, it's 148 picometers. Okay, its bungee cord got stretched further. Now, Lewis theory correctly predicts a double bond for oxygen, but what Lewis theory doesn't do is explain something known as the paramagnetic property of oxygen. Oxygen has some very interesting properties that, again, Lewis structure just didn't predict those, and so because of this, because Lewis theory was not a catch-all, it didn't explain everything. It led to the development of other bonding theories, but Lewis structure was still the initial theory or model, if you will, for determining these structures, and it was the jumping off point. So they all owe their existence to Lewis theory. Now, triple bonds are when we share 6 electrons. We have 3 bonding pairs. As you can imagine, they're even shorter and stronger than a double bond. So, for instance, if you look at that triple bond in the nitrogen, it's 110 picometers. And if you measured 2 nitrogens that have a double bond, they're only 124 picometers. When we look at nitrogen in a natural setting, we find that it exists as a diatomic molecule, very short, strong bonds, that triple bond. And that triple bond is so strong that it becomes very difficult for other atoms to kind of cut in and to break that triple bond. So elemental nitrogen, that diatomic molecule, tends to be relatively unreactive. You've got to put a lot of energy in there to break that bond and to get nitrogen to do anything in that form. This is part of the reason that just nitrogen and air, we have all this nitrogen, but we talk about with crops need to, quote, fix nitrogen in order to grow. They need nitrogen in a different form than that diatomic form because they can't use it. They can't break it apart and then insert an individual nitrogen atom where it needs to be. So plants require a method of breaking that triple bond in the nitrogen and putting nitrogen somewhere else to be able to use it. Okay, just a little side note there. All right, so how do we write a Lewis structure for a covalent compound? Well, the first thing we have to do, okay, and now when you're writing these Lewis structures, I'm giving you steps here. You have to follow these steps in this order. You can't start with step 3 and then go back to step 1, so make sure you apply them in order. you start by figuring out what we call the skeletal structure for the molecule. And this simply is placing the symbols for the elements in relative positions to each other with no electrons. Okay? So, for example, if we look at water, H2O. Okay. In this case, oxygen is going to be in the center, and hydrogen atoms are going to be what we call terminal atoms on the outside. So the skeletal structure that we would draw, we would just write the symbols as HOH. Now, the only way to absolutely know the skeletal structure for a molecule is to examine that structure in nature, but there are some basic rules we can follow in order to be able to determine those. Okay? So this is still working on step number 1, writing the skeletal structure. How do I know what to put in the middle, what to put on the outside? Okay, first of all, hydrogen atoms will always be terminal, and that's because they require only a duet, not an octet. Central atoms have to be able to have more than one bond. Okay, it can't form more than one bond. Hydrogen can't form more than one bond. So hydrogen atoms always terminal. That means they're always on the outside of the structure. They're never in the middle. Second, many molecules tend to be symmetrical. So when in doubt, try to line it up, make it look fairly symmetrical. Okay. So if you have a molecule that contains several atoms of the same type, like carbon tetrachloride, CCl4. You've got one carbon, you've got 4 chlorines. Those 4 chlorines tend to be in terminal positions on the outside. Now, the second guideline has many exceptions. In a case where the skeletal structure is unclear, generally it will, in your book, it will provide you with the correct skeletal structure. I'm going to add a couple of things that your book didn't say. One is, we've talked a little bit about electronegativity. Actually, I apologize, that's in chapter 13. I've looked at it, you haven't. Electronegativity is kind of based on ionization energy that we looked at back in chapter 9. And if you look at fluorine as being the one with the highest ionization energy, it's also the most electronegative. So the more likely an element is to pull electrons toward itself, the more likely it is to be a terminal atom. Okay, so the least electronegative tends to be the central atom in this case. So if you had, say, carbon and oxygen and chlorine in a structure, the carbon is the least electronegative. It's the furthest away from fluorine moving across, so it would tend to be in the center with the other elements around it. Okay, but if it's unclear, generally you'll be given a skeletal structure. All right, so that's number 1. Figure out your skeletal structure. Arrange your symbols of your elements. Step number 2, calculate the total number of valence electrons in that structure. So, for example, if I am looking at H2O, what I would want to do is say hydrogen, I have 2 valence electrons, or I have 2 atoms, I apologize, and each one has 1 valence electron. So I have a total of 2 valence electrons for hydrogen. Oxygen, now this is where you have to be careful. What a lot of people want to do is go back to the atomic number on these, or the atomic mass. This is always going to be the group number. So the number of valence electrons is 1 through 7. That's all you're going to have. Noble gases have 8, but they don't tend to bond. So if you ever did have a noble gas, it would have 8. 1 to 8, those are the only numbers you can have. So oxygen is in group 6A, 6 valence electrons. I have 1 of them in here. So I have a total of 6 valence electrons for oxygen. I have a total of 8 valence electrons in water. If you are writing a Lewis structure for a polyatomic ion, be sure to consider the charge on the ion. For example, if I am looking at nitrate, okay, nitrogen is in group 5A, so 5 valence electrons, and I have 1 of those. And I'm sorry, I'm going the opposite order that I did in the first example. So 5 electrons coming from nitrogen, Oxygen has 6 valence electrons, group 6A, and I have 3 of those. So I have 18 electrons. That's a total of 23. Okay, now here's a clue. If you ever end up with an odd number of valence electrons, that's probably telling you that either A, you did your math wrong, or B, it's an ion and you're missing an extra charge. You can have things that have an odd number of valence electrons, but generally speaking, you should end up with an even number of valence electrons. So in this case, I had the 23, but now here's one more. So if I have a negative charge, that represents an electron. That means I add 1 electron. So now I have a total of 24 electrons. If it were a positive charge, if I had ammonium, I would subtract 1 electron for each positive. So in this case, the number of valence electrons in NO3 is 24. All right, so I have a skeletal structure. I've determined my number of valence electrons. Now I'm going to distribute those electrons among the atoms, giving octets or duets for hydrogen to as many atoms as possible. Let's go back to our water that we had. So this was our skeletal structure, HOH, and I determined that I had 8 valence electrons to play with. Now those valence electrons are like money in the bank. I have $8, I have 8 electrons to spend. I must spend all 8 electrons. I cannot spend any more than 8 electrons. All right, so I'm going to begin by placing 2 electrons between each pair of atoms, just because I know I have to have a bond. I have to have at least one set of bonding electrons, and I may need to come back and fill that in later, but I'm not going to worry about it right now. Now I distribute the remaining electrons. Now first I go to what are known as the terminal atoms. Those are the outer ones, okay, not the one in the middle. Hydrogen only needs duet, so I don't put any more electrons in. Normally I would give it an octet, but in this case I don't need to. Okay, so if I look, I've used up how many in bonding? 1, 2, 3, 4. 4 dots. I've used up 4 electrons. Okay, I've spent that many. I have to spend 4 more electrons, and I have to give everybody an octet if possible. Well, hydrogen doesn't need an octet, so let me go back and give oxygen an octet. Well, look at that. That spends the last 4 electrons. I've spent everything. I'm at a 0 balance. Oxygen has an octet. Hydrogen has a duet, which is all it needs. So good to go. Okay, now that may not always be the case. If an atom lacks an octet, so let me try to think of something right offhand that I can use. So if I have something like CO2, okay, let's just run this one through. If any atom lacks an octet after I've, quote, spent all of my electrons, I go back and form double or triple bonds as necessary. All right, so here's my CO2. When I look at this, my skeletal structure, typically the first atom they write will be the central atom, the least electronegative. In this case, the one that least number, carbon, oxygen, oxygen. That's going to be my skeletal structure. Now, valence electrons. How many valence electrons do I have? Step number 2. Carbon, I have 1 of those, and it's in group 4A, so there are 4 electrons there, for a total of 4. Oxygen, I have 2 of them. Each one has 6 valence electrons, group 6A. So that's a total of 12 electrons. I have no charge. So I have 16 electrons to spend on my structure. I'm going to start, now I'm just going to put them in as a single bond at this point. Remember, I can do that. I can put in a single bond instead of dots, but I have to remember that each line counts as 2 electrons, so 2 lines, 2 electrons each. I have spent now 4 electrons. I have 12 left. All right, now what I'm going to do is start giving the outer atoms an octet. All right, so I gave that one an octet. That used up 6. Okay, that I'm going to move up here. So that left me with 6 electrons. And I can go back and give this one an octet. All right, I have spent all of my electrons. I am at a balance of 0, and this is what I have. Now, when I look at this structure, does any atom lack an octet? Well, this oxygen's okay out here, this one's okay out here, but again, carbon's not happy here. Okay, he doesn't have an octet. So this is where I start forming double or triple bonds by moving lone pairs from the terminal atoms on the outside into the bonding region in between. Okay, now carbon needs 4 more electrons, so I'm going to have to move in, 4 of those lone pairs, four electrons, 2 lone pairs of electrons. I could move them all off of one oxygen if I wanted to. Okay, I could move that in, and I could just have an oxygen triple bonded to a carbon like this, or I could share between the two like this. I hope those dots are showing up okay. Or I could put the triple bond over on the other side. I mean, there's a variety of ways I can do this. Now, which one is correct? At this point, we don't have a way to determine which of these two would be the more appropriate structure, whether it would be the one with the triple bond and the single bond or the 2 double bonds. That would be based on something else that we're not going to get into at this point. So at this point, if you drew either of these Lewis structures, it would be counted as acceptable. There is one, I will tell you, that is going to exist. One does exist, one doesn't. One is more appropriate. You have to do something known as formal charge, calculate formal charge to determine that. But we're not going to worry about that right now. We just want to figure out what's the basic structure going on here, because whether you get the one with the triple and the single bond or the 2 double bonds, those are both going to give us the same basic shape of molecule, which is what we're eventually worried about. All right, sorry, I jumped the gun on that again. I tend to do that a lot. So here's the written out example of that. So the symmetry guideline. Okay, so as we showed, carbon in the middle, oxygen on the outside, calculation of 16 valence electrons, and you may see it better one way than the other, the way I did it or the way the book does it. So it's a good comparison. Okay, we put in our bonding electrons first, okay, just as we did before. Now we put the lone pairs on the terminal atoms, the oxygens. That's used up all of our electrons. Now they're showing moving lone pairs from each oxygen atom into the middle to form 2 double bonds. Okay, again, you could have formed a triple bond and a single. They chose to do 2 doubles here. Now, writing a Lewis structure for a polyatomic ion follows the exact same procedure, but you just have to be careful to account for the charge on the ion when you get your number of valence electrons. Be sure to add for negative charges and subtract for positive. And then when you complete the Lewis structure, be sure to draw it within brackets and write the charge of the ion. That's how you indicate that it is an ion and not a covalent compound. And the reason, I know we said that, we don't tend to do ionic compounds as much. Well, polyatomic ions are themselves covalently bonded. So that's why we show them as a single structure. We tend not to break them apart. They're covalently bonded, but they just happen to have excess charge in one direction or the other. Okay, so that allows the entire covalently bonded structure to then enter into an ionic bond. So it's a little bit confusing, but polyatomic ions have both covalent and ionic bonds to them when they're bonded to a metal. So, for example, if we have the cyanide polyatomic ion, we start by writing the skeletal structure. We have only 2 elements, so we just write carbon and nitrogen. We calculate the total number of valence electrons. So valence electrons in carbon, it has 4 valence electrons, and we have 1 of those. And then nitrogen has 5 valence electrons, and we have 1 of those. Okay, and then it has that -1 charge right here. So we have to add 1 electron to account for that charge. So 4 electrons from carbon, 5 from nitrogen, 1 from the ion gives us a total of 10 electrons. So notice, as I said, if you just added for the elements, you would have 9. That's an odd number of electrons. You're generally not going to have an odd number. You want to have an even number, and that's where it came from. We had to add that 1 electron. All right, so we start by putting our bonding electrons between our structure. Okay, so as we've done here, we put 1 bond in that used up 2 of our electrons. Now we're going to start putting them around the other atoms. And in this case, we only had 8 left. Now, I could have, again, completed the one around carbon and then had nitrogen with just 1. They chose to evenly distribute them. Starting out doesn't matter. You just redistribute the rest of those electrons until you've used them up. Okay, 10 electrons. But what it's telling me is, in either case, somebody needs 4 more electrons. If I did it this way, nitrogen's missing a pair here and a pair here or here. The way they've drawn it, carbon and nitrogen each need 1 more pair, so they're going to have to pull them in, okay, to share all those. So carbon's going to donate 1 in between here. That gets everybody up to 6 electrons, and then nitrogen threw another 1 in, and it got everybody up to 8. Okay, so carbon and nitrogen are triple bonded. Okay, and you can show it as lines instead. Notice that they have put the brackets around the polyatomic ion, and they have included the charge on the ion. Okay. So this is a lot easier to see when you're writing it out step by step. So if you do need to see more of these or need help with that, let me know, and on Friday we can walk through doing several of these structures in the recitation section. Now, there's an exception to every rule. The octet rule is no exception. So what are the exceptions to the octet rule? Well, let's say, for example, we're looking at the Lewis structure for nitrogen monoxide. Now, this is one of those cases, as I said, where you want to have an even number of valence electrons. This one doesn't. It has 11 valence electrons. It has an odd number. It is impossible to write a good Lewis structure for molecules with odd numbers of electrons. Okay, but some of these do exist in nature. They're just kind of freaks of nature. So you just do the best you can. In this case, the Lewis structure gives a complete octet to oxygen, and nitrogen just comes up short 1. It just has 7, and that's just the way we draw it, and it really does exist that way. It really is stable. Another significant exception is boron. Boron tends to form compounds with only 6 electrons around the boron. Okay, 6 is its magic number rather than 8. It doesn't tend to have an octet. So, for example, if you look at BF3 and BH3, both of which really exist, boron does not have an octet. It only has 6. At this point, it's probably better just to kind of remember, these couple of exceptions that you see here. Most of the time, you won't run into that. Now, the other thing you can have is structures that have more than 8 electrons around the central atom. They've got their octet, but they just keep going. When you see this, this is referred to as an expanded octet. Okay, now, just other than to let you know that these things exist, we're not going to really cover expanded octets here. We're not going to draw any of those or look at any of those. Those come into play in inorganic chemistry, a lot of inorganic compounds that are used for semiconductors and things like that. So if you ever got into that and were interested, we could certainly expand on that. You probably will expand on that in further classes, but for this one, just getting the idea of the octet down is going to stand you in really good stead for going on to the next series of courses and for understanding the majority of molecules that you're going to encounter. The majority of molecules are going to go up to an octet, and that is going to be it. Okay? So in spite of the exceptions to the rule, Lewis theory becomes a very powerful and simple way for us to understand how and why elements are going to bond together, and then those molecules that are formed, how they're going to then come together and bond with something else. It's understanding the movement of those electrons. Now, one other thing I want to mention about Lewis structures is that you can have something known as resonance. And this is going back to that example of the carbon dioxide that we talked about, where they were showing a structure that had the double bonds in it, but I said you could also have a single and a triple bond. Okay. Now, when you're writing Lewis structures for some molecules, such as carbon dioxide or sulfur dioxide, you can write more than one good Lewis structure. If we look at sulfur dioxide, we start with our skeletal structure, sulfur in the middle, oxygens on either side. We calculate the number of valence electrons. Okay, 1 sulfur times 6, 2 oxygens times 6, total of 18 valence electrons. Okay, we start by creating one bond between each one. We've used up 4 electrons, distribute the rest. We've now used 16 electrons. Now this is an example we haven't seen. What happens if you put in your single bonded pair, you give all of your terminal atoms an octet, and you still haven't used up all of your electrons? If you still have more electrons, those go on the central atom. So in this case, sulfur gets 2 more electrons, so it has 6. Each oxygen has 8. Now the central atom lacks an octet, so we're going to move one lone pair from one of the oxygens in to form a double bond. Okay, so here's one way they've drawn it. But there is absolutely no reason why we couldn't have formed the double bond with the other oxygen atom. Now keep in mind, these are unique. If we call this oxygen 1 and oxygen 2, okay, I could draw the double bond between oxygen 1 and sulfur, or between oxygen 2 and sulfur. Those are 2 different structures that are equally correct as Lewis structures. And we find that the molecule exists in nature as an average of those 2, that neither one of those individually represents reality. Same thing for the carbon dioxide. Okay, so I can have this existing, okay, oxygen 1 and oxygen 2. I can have this, or I can have this. Okay. So when you get a case like that, where you have more than one Lewis structure that is a valid structure for a molecule, such as in the case of sulfur dioxide, that is known as resonance. Because what's going to happen is, now again, a little bit different in the case of carbon dioxide. You can actually calculate which one is more favored. One of them will be more favored, but that doesn't mean that the other 2 don't exist. They just don't exist in very high quantities. But when I look at sulfur dioxide, there's really not a lot of difference between having a double bond on the left or having a double bond on the right. And when we look at it, we find that both of those bonds, okay, so the double bond and single bond, we don't really have a double bond and a single bond anywhere. What we have is like a bond and a half. They're equivalent and intermediate in strength and length in between. So we don't really have a way to draw that. I guess you could maybe draw it as a full line for a full bond and a dash line for a half bond. And I'm reverting back to carbon here. So what we get is, it's like a 1.5 bond, a 1.5 bond, rather than a single bond or a double bond, if that makes any sense. When that happens, when the bonds are equivalent, you've got 2 things that are valid and they're equivalent, that is known as resonance. And how do we represent that? Well, rather than trying to draw 1.5 bonds, what we draw is both of the structures. Any valid structure is drawn, and then you put a double-headed arrow between the structures to indicate that the molecule resonates between those 2 structures. Okay, keeping in mind the true structure resonates somewhere in between. It's intermediate between those 2. So if you ever see a series of Lewis structures drawn with double-headed arrows between them, that is resonance. Ozone is another example of a molecule that exhibits resonance. So the Lewis structure for ozone consists of this one, where we have a double bond on the left and a single bond on the right, and this one single-double. Okay. Now, if I compare the Lewis structure of ozone to the Lewis structure for diatomic oxygen, okay, that we see right here, which molecule would you think has the stronger oxygen-oxygen bond? Would you think it would be the one that has a double and a single, or the one that has just a double? Okay, well, when we look at that, just the double bond is actually stronger because it's a pure double bond. We don't add the strength of the bonds, we average them. O3 has a bond that's intermediate between a single and a double. So if this is a strength of 2, this is like a strength of 1.5. It is a weaker bond. This is what allows oxygen to actually shield us from ultraviolet light. This is why ozone is so important to us. Okay, so what's happening is we have ozone in the upper atmosphere, and it is capturing these photons that are at a wavelength of 280 to 320 nanometers. That's in the ultraviolet range, and it's one of the most dangerous components of sunlight to humans. Well, now the energy in those photons is just strong enough to break that kind of 1.5 strength bond of ozone. And the energy of the photon gets absorbed in the breaking of that bond. So what happens is ultraviolet light cleaves those bonds. We end up with diatomic oxygen with that stronger double bond, and then we get a free oxygen atom, which doesn't hang around very long. That's a very reactive atom. It's going to bond to something else, but that's what happens. The energy from the photon got absorbed. Now, if I take that same UV light and hit it into this bond of the double bond, it doesn't have enough energy to break the double bond. Okay, so oxygen, diatomic oxygen that we breathe, is transparent to ultraviolet light. Ultraviolet light just passes right by it, and we don't get shielded. It just kind of bounces off and keeps moving. Okay, so if we don't have ozone, if we just have oxygen, we're in trouble with that. All right, so that's an overview of how to draw Lewis structures for covalent compounds, and also the idea of resonance. In the last part of Chapter 10, we'll look at how we can use these Lewis structures to predict shapes. Everything we've done so far, we've been looking at two-dimensionally on paper. We want to start looking at those three-dimensionally, and then lead into the idea of electronegativity and polarity. I apologize, I brought that in a little bit early talking about Lewis structures. We'll talk about electronegativity, what it is, and how it relates to the idea of polarity. So we'll get to the idea of why oil and water don't mix.